We present the work titled Designing Multi-Stage Coupled Convex Programming with Data-Driven McCormick Envelope Relaxations for Motion Planning. In this work, we present the multi-stage convex motion planner with interstage couplings designed by data to address the bilinear constraints to solve multiple types of locomotion problems. Legged robots are versatile compared to their wheeled counterparts as they can traverse complex and discontinuous terrains. However, with open-loop gates, it is difficult for legged robots to overcome terrains that may demand precise footstep locations such as climbing stairs. That is why motion planning is necessary. While a one-shot optimization can take long to solve, depending on the problem, a multi-stage optimization can face circumstances where the earlier stages' solutions can cause the later stages to be left with no solution. Our work retains the multi-stage approach, but uses data-driven methods to find an appropriate coupling between the two stages. In the first stage, we relax the bilinear constraints with McCormick envelope relaxations. Thus, the first stage solves an approximated form of the original problem. We then project the solutions onto the bilinear surface at the second stage. This makes both stages convex, thus the problem can be solved efficiently. Compared to conventional approaches that relax the bilinear constraints evenly into a number of small McCormick envelopes, we use data-driven methods to find the best envelope relaxations, reducing the number of integer variables used while improving interpretability. As the solutions tend to populate at certain regions for the same type of problems, we use clustering and evolutionary methods to identify those regions and fit an approximate McCormick envelope. This is achieved by creating a dataset with random terrain parameters outputting the feasibility of the stages and solutions of bilinear variables. This dataset is used to find high-density regions in the case with the clustering algorithm, while it is used as a fitness benchmark for the genetic algorithm. Both approaches show promising accuracy. To demonstrate the effect of coupling, we show a position-controlled hexapod robot that is climbing up between two vertical walls that has a blue patch with zero friction. The left visualization shows a conventional multi-stage optimization where the first stage has no knowledge of force and finds a sequence of positions that would actually be infeasible as the robot will slip on the blue patch, whereas in the right visualization, the position takes into account the contact forces in the first stage and avoids the zero friction patches. We also tested the planner on the physical hardware. With the envelope fitted from the data when the robot stands on the ground, the planner generates a trajectory for climbing stairs. With the envelope fitted from the data when the robot climbs between the two walls, the planner generates a trajectory for climbing inside a tube. If given both standing and climbing data, the algorithm can identify two clusters corresponding to a single binary variable z indicating whether the robot is walking or climbing. This allows us to minimize the number of integer variables used and maintain good interpretability. Although no motion capture was used to verify the motions, the qualitative success of extreme mobility tasks show the feasibility of the approach.